Okay, I'm going to talk about a thing called the AM-GM inequality. This is shorthand for the arithmetic mean geometric mean inequality. AM-GM inequality. And basically it says that if x and y are both positive, no, they can be 0 as well. This basically says that the arithmetic mean is always greater than or equal to the geometric mean of two numbers. So it's a half x plus y is greater than or equal to the square root of x, y. Which doesn't look like very much. It's dead easy to prove. It's dead easy to prove. I'm just going to start out with the observation that a minus b squared is always positive or non-negative. A squared plus b squared greater than or equal to 2ab. There we go. And I'm just going to write x equals a squared and y equals b squared. And that tells me that half x plus y is greater than or equal to the square root of x. Just get rid of that. X, y. And there it is. So I've proved it. But only for two variables. I'm going to extend it in all sorts of different directions as time goes by and show you thousands of different ways to use it. I just want to make the observation. Let's just try x equals 1 and y equals 2. That's the simplest case we can possibly take. Simplest case we can possibly take. So it's a half of 1 plus 2, I assert, is greater than or equal to the square root of 1 times 2. So 1.5, I guess we could keep it in numbers. 3 over 2 is greater than or equal to root 2, which is of course approximately 1.414, which it is. Oops. But it's quite tight. We've got 1.5 compared to 1.4. It's quite a tight inequality, which shows me that the AM-GM inequality is quite, how can I put this? It's got bite to it. It's only just, it is greater than or equal to, but only just. It's giving us information. Let's just take this numerical inequality here. 3 over 2 is greater than or equal to root 2, and square both sides. 9 over 4 is greater than or equal to 2, which says that 9 is greater than or equal to 8. Well, of course it is, but not by much. Not by much. That tells me that this inequality here is quite powerful. It's got bite to it. It's got, how can I put this? It gives us quite a lot of food. It gives us quite a lot of food for thought. I'm not expressing that very well, but it's quite, it's not tight in the mathematical sense, but it's strong somehow. Strong. We're not wasting any. That's what I'm trying to say. Not wasting much information. Wasting much information. It's a strong inequality. Okay, so what I'm going to do is I'm just going to show a very, very simple example. I'm going to look at x plus. We're going to have x, y, and z all strictly positive. I think they can be equal to 0 as well. X plus y. Y plus z, z plus x, and I want to show that it's greater than or equal to 8x, y, z. Now if you're confronted with this, you would immediately think to multiply these guys out here, to multiply this out. Well, we could do so if I wanted, but it's not very informative. It's a lot easier to take this 8 here and realise what's going on. That 8 there is 2 cubed, of course. So what this inequality is saying is it's the same thing as a half x plus y times a half y plus z times a half x plus z. That's the left hand side. So the left hand side equals this. I'm trying to prove the left hand side is greater than or equal to the right hand side. So we know that the LHS is the product of three distinct arithmetic means. So the left-hand side, everything is positive here, or at least non-negative, is greater than or equal to root xy times root yz for this term times root xz, which equals xyz. There you go. So that's it. It's just dropped out. I think that's really rather neat. And I'm going to stop there.